Hi, in this video I want to show you how to compute probabilities for normal distributions. There's three situations I'm going to demonstrate in this video. On the calculator I'll be using the normal CDF function, and that is in the distribution menu. And the distribution menu is the shift function over the vars key. Let me show you where the function is. You can see it's when you go to the distribution menu in this first submenu, it's the second item down, normal CDF. Okay, now let me set up the example I want to do, and I've got a worksheet here showing you a normal distribution for which the mean is 24 and the standard deviation is 2, and what's shown is a shaded area from x equal 22 to x equal 26, and that represents the probability that the random variable x will have a value between 22 and 26, and this worksheet computes that value to be about 68%. And that's in agreement with what we know about the empirical rule. Now let me show you how to do this calculation on your calculator. With normal CDF and a random variable x, it's going to take four inputs. The first two inputs are the range of x values that you're interested in. So the first value would be the lower value of x, 22, comma, then the upper value of x, 26, comma. Then you want to give it the mean of your distribution, 24, comma, then the standard deviation. Now when you press enter, you're going to get the same probability, about 68%. So that's very basically and very simply how normal CDF works. I know a lot of times students will take the x values, 22 and 26, and then they'll compute the z-scores and then use the calculator to find the probability. That's an unnecessary extra step. The calculator will take the x values, compute the z-scores for you, and then find the area or probability. Let me just do another quick example to kind of reinforce the idea. So I'm going to put in 22.7 and 27.2 to show you how that works, and you can work along with me as I do this. I'm going to take the normal CDF function, again the lower value first, 22.7, comma, the upper value, 27.2, then the mean and standard deviation. And I get about 68.7% roughly, which is in pretty good agreement with the worksheet. I know there are occasionally a few differences in the answers at several decimal places out, but you can rely on your calculator to be pretty accurate, more accurate than, say, your statistical tables, so this is the better way to go. But right now for this example, the computations seem to be in good agreement, about 68.74%. The next example I want to show you is the situation where you're looking for the probability that x is less than a value or that x is greater than some value, and in that situation the shaded area will extend out either into the right tail or the left tail. So let me bring up a worksheet that shows that situation. Okay, I've got here a normal distribution again, the same mean and standard deviation, but now I'm looking at the probability that x is greater than some value. And what's shown is the probability that x is greater than 26, and it computes that to be about 15.9% roughly. Now how do you do this computation on your calculator without a finite or specific upper limit for this range? What you can do is, let me grab the function out of the menu. We know the lower limit is 26, so I'll go ahead and put that in. Now for an upper limit, a lot of books will tell you to use something like 1 times 10 to the 99th, and that's about as large a value as you can put into your calculator. So that's sufficient for any situation. But it's a little tedious to have to go find that shift key to enter times 10 to the 99th. But let me finish this computation. I'm going to go ahead and put the mean and standard deviation in and then press enter, and you get that same probability, about 15.9%. What would also work in this case, and a value I use quite often, is 999 to indicate a value way out in the right tail. So let me show you what you get if you put that in. And you get the same probability. The idea is you want to put a value that's several standard deviations away from the mean. In this case, I would go at least 6 standard deviations away from the mean. With a mean of 24 and a standard deviation of 2, 12 units out would put me at about 36. And at that point, you should be far enough away into the right tail that the change in area probability is negligible, and you'll get the same result. So let's take a look at what we get when we do it that way. So 26, 36, again a value way out in the right tail, about that's 6 standard deviations away from the mean. And if I enter that, I get out to several decimal places the same probability that I got using either 999 or 1 times 10 to the 99th. So again, what I wanted to point out in this example is when you have a situation where x is greater than some value, for the upper limit, make sure the value you choose is at least 6 standard deviations away from the mean, and you'll be safe with the value you get out to at least 5 or 6 decimal places, which is usually sufficient for coursework. The same thing applies when you have a probability extending out into the left tail, and that would be a situation where x is less than some value, and again you would use a value extending out in the tail, either negative 999, or in this case 12 would be far enough away into the left tail to compute the probability accurately. Okay, so that's the second type of example I wanted to demonstrate. The last one I want to show you how to do is a situation where you have the standard normal distribution and you're working with z-scores. So let me bring up a standard normal distribution curve. Okay, here's the standard normal distribution curve. It has a mean of 0 and a standard deviation of 1. What's shown is the probability that z falls between -1 and 1, and again, in agreement with the empirical rule, the probability comes out to about 68%. Now these are great, or very simple calculations to do on your calculator. Again, I'm going to grab the normal CDF function. When you're computing a probability for a standard normal distribution, you'll enter your z-scores in the same way that you entered the x values. And let me go ahead and show this to you. I'm going to put in -1 and 1 to demonstrate this particular problem. When you go in to put a negative value, be careful that you use the negative sign key and not the minus sign. It's the negative key next to the decimal point at the very bottom row of the keypad. So -1, 1. Now that's all you have to put in. If you don't specify the mean or standard deviation, it's going to default to these values. It's going to assume basically that you're doing a standard normal distribution problem. So when I press enter, it returns the value accordingly, 68%. And let's just change this example a little bit to show you how that works. So -1.4, let's say, to 2. Again, normal CDF, -1.4, 2, enter, and it computes a probability of about 89.6%. So a very convenient way of computing probabilities using your calculator. It's quicker and it's going to be more accurate than using statistical tables to do the same work. Although there's a lot of value, I think, to trying and using the tables a few times. It helps you to gain a better understanding of the underlying calculations, what's going on basically behind these keystrokes. Anyway, that's what I wanted to show you about this calculator function normal CDF. In the next video, I'm going to show you how the function inverse norm works, and it's kind of the inverse operation of what I've shown you here. In those situations, you're actually given the probability or the area under the curve, and you're asked to find the corresponding x value or z-score for that situation. So I hope you found this helpful. Thanks for watching.